In this session, we're going to go ahead and take a look at digital communications. We're going to look at serial communications in particular because that's the way most data is transmitted. So let's go ahead and take a look here. So the two different methods obviously are serial and parallel. And so serial, we are sending one bit at a time, sometimes pretty fast, sometimes slower, but parallel is allowed to send multiple bits in one clock tick or one clock cycle. So, but there's many different types of serial, trying to get faster and faster and faster using single bits. So some examples you might recognize: RS-232, Ethernet, cell phone, 802.11. So these are all different types of serial communication protocols that are used all the time. So in serial data communications, a byte is serialized using a parallel and parallel and serial out shift register. That's very difficult to say. Transmitted over a single wire to a serial in parallel out shift register. So even though you may have data that's coming in quickly and you can load it all into a register and you can send it out a bit at a time, and then on the receiving end it'll receive it in serial and then parallel out. So that's typically how things operate. It's the most cost efficient. Every time you add a line, you are incurring an extra cost. So parallel transmission is very, very expensive. Serial communication much less expensive. So if you're on a telephone system, an old telephone system, it must be converted from zeros and ones to audio tones. So it says this is done by a peripheral device called a modem, and that's just a shortened version for a modulator demodulator. And same thing for DSL. It's just a faster scheme of the same thing. So this is not true, though. It's not converted to audio for cell phones, though it still gets modulated onto an RF carrier. So that's a whole different discussion. But the ones and zeros have to be converted somehow. So you have to have some protocol in place and some setup where the transmitter and the receiver are on the same page as in terms of what happens. Here I'm ready to send, here I'm ready to receive. Okay, here comes the data. So we're going to look at how that happens. So there's two types, and this is kind of falling in line with talking about flip-flops in general or counters in general. We typically have either a synchronous or an asynchronous operation. The difference between the two is that if you have a serial synchronous transfer of data, that means that the block of data is also sending a clock signal with it. Asynchronous means that even though the transmitting end is operating off its own clock, the transmission is essentially asynchronous because the receiving end may not have the same clock as the sending. So there is no separate clock wire, and so you have to have some type of protocol set up on both ends to make that happen. Otherwise, you have to send the clock wire as well. Okay, so that says there's many different chips available for serial data communications, and they usually have one of these two designations, either a USART or a UART. So the USART is the you can configure it to do whatever you want. It's the universal synchronous asynchronous receiver transmitter. So it can do either mode, and it can be either on the receiving or the transmitting end. And then the UART, which is more common, is the universal asynchronous receiver transmitter. So same thing, it can operate on either end, but now you don't have the synchronous option. Okay? So there are a couple different ways that we can talk about how devices talk back and forth. And so usually I use a couple different examples for this. So simplex transmission would essentially be what's happening right now. My voice in this video is the transmission signal, and you, with your eyeballs and your brain, converting it into something you understand, are the receiver. Okay? So, obviously it's going through a whole lot of different steps before my voice reaches your ear, or, the light from this transmission reaches your eyes. But it's that simplex transmission where it's going only in one direction. You can also think about it like broadcast TV or broadcast radio, where you just have to have a receiver and put an antenna up in the air to catch the signal. Okay, so that's a simplex transmission. Half duplex means that now you can have the either end of the transmission be the transmitter or the receiver, but only one operation can be happening at the same time. So I liken this to the old Nextel phones. I don't even know if they're still used anymore, but the old Nextel phones were essentially, kind of like walkie-talkies on something on a different level, right? So, you could have instant communication with anybody, and they could be anywhere. They didn't have to be close to a CB station, because that kind of transmission has been around for a while. If you know anybody that drives a semi truck, the CB radios that they use, only one person can be talking at once, but anybody can be the transmitter or the receiver. Okay, and so it's the same thing with the old Nextel phones. Only one person could be talking at one time, and then the other person could respond. But only one person could control, one end could control the transmission path. With full duplex, that's like answering a telephone, right? So you've got the transmission going to the receiver in both directions at the same time. Okay? So simplex transmissions, broadcast, half duplex, only one end can transmit at a time, and full duplex is both transmitters going at the same time. So it makes things a little bit quicker. Okay, so again, why would you choose one or the other? It depends on whether or not the data transfer can be simultaneous. So you just have to set up the best system for what you're trying to accomplish. So it says full duplex requires 2 wire conductors for the data lines in addition to the signal ground. One for transmission, one for reception, in order to transfer and receive data simultaneously. Anytime you add more complexity, or if you add more wires or signals, you're going to increase the cost. So one of the most important parts of this is the data, what we call the data framing. So if you don't have a plan in place that says, okay, I'm going to send you, my data bit stream is 7 bits or it's 8 bits. I can decide how many pieces of data I'm going to send to you. If I don't need that extra bit, then I'm not going to send it. But I have to have a protocol set up with the receiver, and how many bits are sent at a time, and sort of like a package. So there's always going to be one start bit. So it says in an asynchronous transfer, each byte is placed between a start and stop bit. There's always going to be one start bit. That lets the receiving end know, okay, the transmission is about to happen. So the start bit is activated, and then the data is transmitted, and then on the back end of it, there's a stop bit. Or there could be 2 stop bits, just depends on what protocol you have set up. So that adds a few more bits to the stream. Okay? So this is what it looks like. So this is the ASCII character A. And so if you were to look at that in binary, that is essentially 01000001, right? 41 in hex. So you can see here, we're waiting, and then finally we have the, what we call the mark. That's us waiting. And so the start bit hits, and then we have our data transmission, D0 through D7. That's our 8 bits or our byte. And then we have the final stop bit, okay? So it says transmission begins with a start bit followed by D0, the least significant bit, and the rest of the bits until you have the most significant bit. So again, you can see here's the start bit, here's 1, 0, 0, 0, and then 0, 0, 1, 0. Okay. And so for any character on the ASCII chart, whatever the binary equivalent is, it's going to look like this every time. Now, in this particular example, the data framing, the protocol suggests here that there's only, there's one start bit and that there's one stop bit. If the protocol was 2 stop bits, that would be 11 bits total. So again, you have to know whether the data width is going to be 7 or 8 bits. That's the two typical transmission sizes. And you either have 1 or 2 stop bits. Now here's the other thing. You can also have a parity bit, and this pulls back into what we talked about in previous chapters. So the parity bit, remember, is to ensure that the data transmission is not corrupted. You can have odd parity, you can have even parity, or you can have you don't have to have parity if you don't want to. Okay, but remember, parity is there to check and see if there's the same number of highs and lows on highs. Whether there's an odd number of them or an even number of them, and then checking that on the back end, on the receiving end. So if you had 8 bits and you had a parity bit, so it's possible here that you could have 11 total bits, or 12 total bits, because there's a stop bit that's in front of this. So stop bit, and you could have up to 8 bits, that's 10. Then you could have 2 stop bits beside that, and then one of those could be a parity bit. So whatever the case may be, but you can program the UARTs for any of those operations. We also need to talk about how quickly things happen, which is called the data rate, and that's the rate of data transferred stated in bits per second. But just because we say BPS and baud, they're not necessarily equal, although they are often. So it says asynchronous serial data communication rate is generally limited to 100,000 bits per second. Okay, and that's just, we talked about propagation delay and things like that will limit the quickness with which you can use these protocols. So the baud rate is the bits per second. How quickly is it sending the data? Is it sending 50 bits a second? Is it sending 1,200 bits per second? So obviously the more bits per second it sends, the quicker the system is operating. One of the serial communication standards that we use is the RS-232, and this has kind of been phased out to some degree because USB has taken over, but this was created back in 1960, and there are still some computer systems out in industry that use RS-232. If you go to most university labs these days, the PCs won't even have a US or an RS-232 connection. If you want to have an RS-232 connection, you have to put in an external serial card. It'll be internal to the computer, but you have to buy an aftermarket serial card to even get that connection because of, like I said, because of USB. So it says, because the standard was set long before the advent of TTL logic, voltage levels of RS-232 are not TTL compatible. So, and this has always been kind of backwards to me, right? So a 1, or what we call the mark, is a negative voltage between -5 and -15, or it could be -3 and -15, depending on which book you read. A 0, or what we call a space in RS-232, is actually a high voltage level between 5 and 15, or some books will tell you 3 and 15 volts. But just, it's, if you just want to remember, the 0 or the space in this logic is actually a positive, and the 1 is a negative. So it says, to connect RS-232 to TTL or computers requires voltage converters such as the MAX-232 to convert TTL logic levels to the RS-232 voltage. Okay, and so these are typically called line drivers. So you may have a computer still at your home that's maybe a little bit older that's got one of these connectors on it, and there's 2 different types that we're going to look at. So here's one of them. This is what they call the DB25, or the 25-pin connector. And so, it's configured, starting from the top left. If you look at the slants that go toward each other here, towards the bottom, 1 through 13, and then 14 through 25. And then here, it's got a listing of all those different lines. Okay, so, part of the reason why we use serial communication is because it's too expensive to do things in parallel, because it requires too many lines. Well, look where we ended up here. So, a lot of these aren't even used. A lot of these lines are not even used. You can see there's a few of them that are unassigned. So, to rectify that and to try to condense this down, they went to the DB9 connector. So IBM is the one who introduced this one. Now you're down to only 9 spots, 9 lines in the cable, and it became the serial input-output standard. So you can see the different types of things here. Data set ready. It's a lot of this. Okay, are you ready? I'm ready. Let's send data. Right? There's like I said, there's a handshake with the protocol. So went from a lot of these, and a lot of this is double checking secondary data carrier detect, secondary clear to send. There's a lot of backup here that makes this a really robust connection, and makes error detection pretty easy to solve. But there's 25 pins, so that means that there has to be 25 wires inside that cable. So a null modem connection, if you don't have a modem at all, you can connect to computers by using a twisted pair Ethernet communication. So part of what you may have to do in your EE or EET career is network 2 computers together without using Windows 10. Now, 15 years ago, let's say 2005-ish, as this is 2020 when this is being recorded, 15 years ago, it was very common to, in close settings, connect them like this. So you had a direct connection. Well, Windows 10 has made networking so easy that pretty much anybody can set up a home network connection and have access to public folders and files on different computers. But this would be a way to hardwire it if you did not have the modem set up. So here's some more on the RS-232 handshaking. Says, for fast, reliable data transmission, data transfer must be coordinated. Okay, so everybody has to be on the same page. I would say most pins of the RS-232 connector are used for handshaking signals. Now, like it says here, often these were not used, and the whole point of serial was to save wires and money. So the older 486s had ports designated COM1 and COM2, and so if you have an older computer, if you use them 20-25 years ago, if you had to go in and figure out why something didn't work, you might look at the serial ports, and the first 2 were always RS-232, COM1 and COM2. I remember, having issues myself back in the day trying to figure out which one mapped to which connector. So, however, in recent years, and I would say probably the last 10, maybe 10 to 15, one of these has been replaced with a USB port, and then you still had one RS-232 connection on your device, your PC or your laptop. So it says, in the absence of a COM port, a COM to USB converter module can be used, and that still can happen. So if you have an older device that only runs off RS-232, there are connectors that you can use that will convert it to USB. So, and if you've bought a PC in the last 5 years, I have not seen any RS-232 included. If you want RS-232 on a new PC, you have to buy an extra card. So, USB has pretty much phased out that technology altogether, even though RS-232 is still used in industry, which is why it's important to understand the protocol. So, again, because RS-232 voltages can vary from -15 to +15, you have to have a line driver to convert down to TTL voltage levels, because TTL is, 0 and 5. It makes it super simple. Right, but RS-232 was done well before that, so that's why they don't play nicely together. So it says the MAX 232 has 2 sets of line drivers for transferring and receiving data. So you may look on, even on your Altera board, you have these T and R, usually TX and RX pins on there, and all that is the transmission and receiving pins. Okay, and a lot of times you'll see the T and the R have little LEDs next to them, and they'll blink, letting you know when there's either a transmission or a receiving action happening. Okay, so typical baud rates for the RS-232, 1200, 2400, they usually follow this doubling, 1200, 2400, 4800, 9600, on down the line. And So, you know, if you have an older version of Windows, I don't think Windows 10 does this anymore, or they do and they've called it something else, and I haven't yet checked to see what it is. But, you know, you used to be able to look and see what the baud rates were in Microsoft Windows Hyper Terminal for your communication ports. So, you know, now that everything is USB, the last time I checked Windows 10, there was, you know, I didn't find Hyper Terminal or a communication settings, you know, that I could monitor this. Now, you can look at the speed of things in your task manager. And maybe that's where they have it now, and I just haven't found it. But anyway, these are the different baud rates, how many bits per second, and again, this has to be established before any data transmission happens by the transmitter and the receiver. If you want to learn more, there are a couple of more websites, and these are in the PowerPoint, and you can also just type these in if you wanted to. This one right here, the serialportmonitor.org, it's really good. It's a short one, but it essentially just recovers or restates what has been said here already. So there are some other serial options, and I'm not going to talk about USB as much, but because there's plenty to say on USB. You could, there's three different. There's USB 3.1, I think, is where we're at now, and that is I think it's a 600 and some megabyte per second transfer protocol. It's something ridiculous. You can have a full 2 hour gigabyte 8 gigabyte movie downloaded in maybe 10 seconds. It's super quick. But this one uses 4 wires. It's got a 5 and a ground, and then it's got its differential data, which is the magic that makes the USB work so quickly and efficiently. And so you can read more about that. I'm not going to get into the details of this and quiz you on this part of it. The biggest thing, though, is really looking at the data framing and seeing how that can be done. Okay? So I just want to say something briefly about the RS-232 protocol in terms of the voltages, because it's a little bit backwards from the way we think, and I've wanted to show you this graphic. This is actually in a document in your module called Serial Short, and it's right next to the one that we just opened. RS-232 uses anywhere from positive 15 volts down to negative 15 volts. This depends on the system. And the key thing, though, is that the positive voltages are used as a logical 0, and the negative voltages are used as a logical 1. So that's a little bit backwards from the way we think. But here is an example of sending an ASCII K, which is 4B in hex if you look at the ASCII chart. So that is 0100, and then B is 1011. So that would be the total 8 bytes here. Now, when we're sending ASCII characters, you could also just send 7 bits instead of 8. And we talked about how you would frame that. Are you sending 8 bits or are you sending 7? But if we were sending 8 bits and we had one single start bit and a stop bit, this is what the transmission would look like in RS-232. It's a little bit different than the PowerPoint slide that talked about data framing, because that only looked at things in terms of ones and zeros. So if you were to look at that, look at this same example, you would have to flip it top for bottom, end for end, to get what it would look like in that other chart. So this is very specifically an RS-232 transmission. So you can see here the positive voltage and the negative voltage. So we sit at the negative voltage at rest. And so it's what we call idle. It's waiting for the transmission to happen. Then it gets the low. Remember, this is up here. The positive voltage is low. So it gets the initial low, and the transmission knows, okay, now the next 8 bytes, because that's the protocol we've set up, the next 8, bits, not bytes, the next 8 bits are going to be the data transmission, and then there should be a logical high to end this data stream. So there's going to be 10 bits total being sent here. So again, we sit idle, we get the start bit initially. Now you can see the bit stream here goes from least significant bit to most significant bit. So if we read these backwards, that's what the ASCII 4B would look like. So again, if I type in the binary here, that would be 0100, that's for the 4, and then the B is 1 0 1 1. So you can see here, if you read this left to right, then it's going to look like it's backwards. But the reason why it's doing that is because it sends the least significant bit first over the data transmission. And again, you're typically parallel loading in on the shift register on the transmission side, and then you send it serially out. And then on the receiving end, you serially receive it in, and then you parallel load out from there. So, but the actual transmission part of it is serial. So just wanted to show another example of data framing without just using the logical ones and zeros, the actual voltage levels when RS-232 is communicating.